All right, good morning.
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 Welcome back to text mining. So I check, so I don't know how many of you are choosing to do a project or a thesis. So how many of you is going to take, so if you, maybe this is easier. Can you send me a chat if you choose to do a thesis, sorry, to do a paper option, or you want to do a project option? Okay, so research, yeah, so any one of you is doing a project? Okay, so, and also I checked the discussion board. Some of you ignore the discussion board, but that's okay, but you I just want to make sure that you understand participation in the discussion board contributes 5% towards your final grade. Okay, so just want to make sure you understand that. And all right. All right. Okay. So are there any questions for me?
No question. Thank you.
Okay. All right. So we are going to continue our topic on web search or search engine. So far we have talked about text retrieval. And of course, one of the biggest applications is search engine. So we all know that on the World Wide Web, you have lots of text documents and other documents on there. So you just need to develop a crawler to collect data. And then you need to make an inverted index so that you can do search quickly based on the query. So whatever we have learned earlier before before this module can be applied. The things that are new for web search is that the inverted index file is too big to be placed in a single machine's main memory. So which means that it needs new technology to handle such things. So Google's approach is to develop a new file system called Google File System. And based on that system, it develops a programming platform called MapReduce, which is a parallel platform. So basically, it just provides an interface for programmers to write programs without really worrying about the underlying mechanisms for carrying out parallel computation. So last time we looked at a conceptual level, what this MapReduce is doing. And also, of course, the Google File System. So today we are going to just look at the web structure without worrying about queries. So we are going to just look at web structures. Okay, so by just looking at web structures, we could actually rank nodes, right? We know that some of the pages are more popular than the others. So how can we rank pages? So we're gonna look at rank pages. Depending on the structure, okay? So it's not depending on hits, right? So not depending on how many people are looking at a certain page, but we're just looking at the structure of the page. Now, what is this web structure? So now just look at this. So we're going to first come up with this web structure. So that's by link analysis. So in other words, on a web page, okay, so on a web page, let me start a whiteboard here. So let's say we're looking at single web page. Okay, so the structure of a web page would be you have some of your text, you have some of your images, videos, that kind of thing. But then usually you will have links. You will have links. So these links will be scattered around in your page. So this means that for further information, you're going to see this page. So then this link, you can treat each link as a pointer to a different page. So there's a pointer. And of course, some of the page may also point it back, right? Some of the links, and then this will further, and it may be cross linking. So maybe there's a link here, go in here, right? So by looking at this, then you know that it is a gigantic graph. So this web is a huge graph. Huge directed graph. So by just looking at these links, and of course, how do we represent a graph? Of course, we use adjacency matrix. And that is huge, obviously. This adjacency matrix is so big to be placed in a single machine's RAM. Hence, you still need to use a map reduce to handle it, right? So we're not gonna look at that detail because that is a huge thing doing by a company. So Google does that. So, but the underlying technology to carrying out this computation on on a matrix this big has to be parallelized, okay? So we're not gonna look at the parallelism, we're just looking at the conceptual level. How can we rank a page? Okay, so on this huge directed graph, right? So this is a directed graph. How can we determine whether one page is more important? By important means it's more popular than the others. Okay, so that's our concern here. So now let me go back to the slides. Okay, let me go back to the slide here. Okay. So by looking at this, the structure of a web page, we can have two concepts. One is what's called a hop. The other one is called authority. So in the extreme case, so let's call it the extreme case. That hops are a page that only consists of links going out, right? So that means that this is a hop. So that only consists of links going out, but of course, some other page, once they realize you are a hop, they may want to point. So in their page, they may include a link to go into this hop, and hence a hop can also have incoming links. However, we're just saying that at the extreme case, okay? So extreme case, a hop consists of only links going out, and in the extreme case, an authority is a page that consists of links that go in. So why it is called authority? Because it's important. All the other pages will have to reference this page, okay? Because the information there is also is official or some kind of authoritative, right? So, but then of course, in reality, there is no such extreme case, because authority, even though it's authority, you may still have a link going out. In modern days, of course, you also have advertisements. You also have some other links that you want to point to. So there is no pure hop or pure authority in today's web structure. But nevertheless, a page that consists of more outgoing edges, substantially more, right? For instance, like 90% are outgoing and 10% are incoming, then you can think of that as a hop, and an authority node may consist the opposite, 90% incoming and 10% outgoing, right? So of course, if it's a half and half, then they are both hop and authority. Okay, so basically, that's the concept of hop and authority. So then we have two things now. So one is, how can we just rank nodes based on links? The other one is, how can we use hop and authority to compute ranking? So that comes with two algorithms. Okay, so we have two algorithms to do this. The first algorithm is called PageRank. Okay. PageRank was an algorithm that came out of a PhD thesis by the Google founders. So they actually did a PhD thesis at Stanford. That actually one of the things they talk about there is PageRank. So PageRank is an algorithm that ranks nodes on a directed graph, okay, based on links. Okay, so this is really a ranking algorithms. On a directed graph based on edges or links. Now let's call it links. Okay, and the underlying mathematical principle, or the foundation, is a Markov chain. So this is a Markov chain. Okay. So there's a mass branch that's called Markov chain and or stochastic process, and that actually provides the mathematical foundation why this algorithm would converge. Okay, so that we're not going to talk about this. We are not talking about Markov chain, but I'm going to point it out that it has a solid foundation behind this. Okay, so now let's just look at how this algorithm is doing, what this algorithm is doing, how it's done. Okay, so let's just look at a very simple directed graph. So we're going to look at this 4-node directed graph. Of course, in reality, this is huge, right? The millions of nodes, right? So the entire World Wide Web will be one single graph. So that's it's huge, right? So, but for the concept, right, at the conceptual level, whether it's huge or small, the concept is the same. So we have this graph, and then we're going to use a transition matrix to represent this graph instead of using adjacency matrix. So when we look at transition matrix, that comes from the concept of Markov chain or stochastic matrix. So in particular, we're going to sum each row up here. So each row, when you sum them up, should be equal to 1. Right, so each row when sum up is equal to 1. So what that means here is that if you have multiple links, then each link carry the same weight. Okay, and then you sum them up, it's less than, it's equal to 1. For instance, for D1 here, for this node, it has a link to go to D3, and it has a link to go to D4. Hence, you have 2 links, and then they carry the same weight, sum them up is equal to 1. So that means that the weight on this link from D1 to D3 is 1/2. From D1 to D4 is also 1/2. So that's what you have here. And then for D1, it doesn't go anywhere. I'm sorry, for D2, it goes to D1, right? So for D2 here, it goes to D1, but there's only one link. So all the weight that will be given to that link. Similarly, for D3, it only has one link that going to D2. So all the weight will be put on that link. And on D4, you have 2 links. So then this is the 1/2, this is the 1/2. So that's called a transition matrix. Okay. So the things here for this matrix, for this transition matrix means that each row you sum them up is equal to 1. Okay. Of course, if you take the transpose, that means each column is summed up to 1. Okay, so that so far has nothing really to do with PageRank, right? So this is just a standard Markov chain process. Now they observed, right? So the following things. This is an observation that how do you say a page is more important than the others? So their thinking here is this: a page here. Maybe I'll start a whiteboard. the importance of a page is influenced by the pages that point to it. Okay, so this is their observation. Observation 1, the importance of a page is determined by the pages that point to it. So that means if let's say I am a page and then you have incoming edges, you also have outgoing edges. Okay, so to determine my importance, of course, obviously, it's not because I have lots of links going out to the other pages. It's because there are a lot of pages that point to me. That means I'm important because they have to call me up, right? So I'm kind of authority, right? So that's the concept of authority node. But then if this page is important, so if it's important, then of course I will be my importance will be increased because this page is important. Just like now we have this concept called as a VIP node, right? So if a VIP node points to me, of course, then I'll be happy because that means I am important because that VIP node points to me. So that is their first observation. The reason then, because they are important, more people would tend to visit that site once they are on that site because they have a link to me. Then I have a much bigger chance that somebody can visit my page. Hence, I will be important too. The second is that for people to browse the web, sometimes, of course, they always have a beginning URL, just like you do a quarter. So they really have the beginning ones. So of course, how do you choose the beginning ones? And sometimes you can use a query, okay, or you can use a random jump. Right, so how do I? Well, actually, query is it's these things, right? You go to a search engine, you put in your query, and you're going to be returned a rank list because of the underlying search mechanism. But then you can also randomly jump into some web page and then start from there. So you have a random jump. So then there's a PageRank algorithm takes these two things into consideration on a transition matrix. Okay, so how do you put them together? Basically, so the algorithm itself is pretty straightforward. The challenge, of course, is how do you carry out this computation when this matrix is so big, right? So, but at the conceptual level, it is not hard to understand this algorithm. As a matter of fact, it is one of the easiest algorithm if we're going to teach it in the graduate level algorithm course. But of course, there we didn't talk about stochastic algorithm, but it shouldn't be too hard to understand. All right. So now we put these two things together. The first part is from the nearby, or from my neighboring pages that point to me. So I want to compute DJ's rank. Now this P represents PageRank, and this T+1 means now this algorithm is a iterative algorithm. So you have an initial value, let's call this T, and then the next one, this is how I'm going to do it. So this is the standard Markov chain algorithm manipulation, right? You basically just multiply this matrix again and then again. Each step you multiply this transition matrix once. Next step you multiply it another time, and so on. So you keep iterating these things and until your result converges. So now for the first part, so DJ, so I'm going to look at DJ. This is my document. Well, I would use a page one, but since we use a page rank to represent the rank or the probability, right? So we already use P, so we didn't use the page rank there. So for DJ, what I'm going to thinking is that I'm going to look at every nodes that points to me. So let's call this a DI1, DI2, DI3, blah, blah, blah. So all of them, they have their own rank. So this is their rank, right? Assuming they have a rank. At the beginning, you can just choose random value for these rank. Stochastic theory indicates no matter how you choose your initial value, they will all converge to the same values. The only difference is that how fast this convergence will take place, right? So we randomly choose initial values. It doesn't matter. Okay. So this indicates all my neighboring nodes that points to me. Okay, so let's say you have n nodes. So this will be the page rank that points to me, and then this Mij indicates their weights, right? So really you have this transition matrix. So basically you are going to so you are going to say that this is I Ij, so Mij indicates the i's row and the j's column value. Okay, so this is from I to j. That's the i's row, j's column means that the weight that carries from I to j. So that's Mij, so put that weight there. So you put the weight, you sum them up. So there I have this portion. So this is standard Markov chain stuff. But then I also need a model, the second part, I model random jump. So how do you random jump? So that means that I'm going to treat every page equally likely. They have the same probability to be selected from. So hence you use a uniform distribution. That's 1/n. So each page is equally likely to be selected because it's a random jump. And then, of course, these are the previous value. And then you have two components. I want to combine these two components, yet I still want them to be a probability value. So that means that I have to put a weight. So I have to put a weight to it so that, of course, this alpha is greater than or equal to 0 and less than or equal to 1. So when 1 minus alpha plus alpha is 1. So the whole thing then is still still a probability. So in other words, you didn't destroy the property of a transition matrix. So that's it. So that basically is the idea of this PageRank algorithm. And then you keep iterating it by choosing initial value of PageRank for each node, right? So let me start a new. Okay, so the first thing is select at random. And initial value, initial value for each page's rank, of course, between 0 and 1. And then you got to select alpha, and then you just keep multiplying the transition matrix, keep iterating, right? Because what we have earlier is a recurrence relation. So we just keep iterating it. Keep iterating the equation, right? So the recurrence let me just repeat. Let me rewrite this now. Repeat. Repeat. It's not really recurrence relation, but we can just say previous equation until converges, until it converges. So that means that when for each page, when it's a previous value and the new value is the same. But of course, since we may never end up the same, but so that means that we have to set up a threshold. So when that happens, I stop, right? So this epsilon could be small, like 1/1000 or 0.00000 point something, 0.00000 something, right? So this is a small. So that's what it means by it's converged. And we, as we mentioned earlier, that the theory of Markov chain indicates that this will converge as long as certain conditions are met. So we're not going to mention the general theory, but for this PageRank matrix, the way it's constructed makes sure that it converges. So it will converge. It's just that you don't know how long it's going to take, but usually it's pretty fast. Okay. And how do you select alpha? So alpha is selected by default. Alpha is 15%. So that means that about 15% of time you random jump into a page you start with your browsing. Okay, so basically that is the algorithm. All right. Okay, because it puts weight on its neighboring nodes that point to you. So it really is to capture authority pages. Okay. So now let's look at an example. More details about this example. All right, so this is what we have from the previous one. So now we're going to write it into a vector. We're going to write into a vector notation. So now this is a P, so this is a vector. And you write it up, it becomes this equation. So this vector P is equal to alpha times a unit matrix plus 1 minus alpha. So this is called a, usually we use a D to represent it. I think I have this. Yeah, I have in my previous slide. So we usually use a D represented. So that D comes from a word damping. So this is called a damping factor. Okay, so usually we put a D. So this is D. So this is 1 minus D. You can also think of this as 1 minus D plus D, right? And then multiply M, and then you take the transpose, and then the fact, and then this the matrix. So this is the earlier value. This is a new value. So you keep iterating this thing until it converges. So in our example, what we have for this matrix A, we call this matrix A. So what we have is this. Okay, so you take alpha to be 0.2, just for easier calculation. The default value is 0.15. Okay, so this is easier calculation. Okay, and so you could verify that when you do this, when you add them up and take the transpose, now each column should be sum up to 1. So each column is sum up to 1, right? So you can see that. So then you can just keep repeating this, and then you get, when it converges, then you get the value for each node. So you get P of D1, P of T2. So that's a ranking of that node. So that's ranking of that node, that's ranking. Okay, so this is a PageRank algorithm. So as I said, the concept is not hard. If you know the underlying statistical process that guarantees you that this process will converge. The challenge, as I said earlier, is how you carry out such a huge computation, because this transition matrix is huge. And then, of course, Google use MapReduce to do this. Okay, so it captures, as I said, it captures authority nodes. And what happened about hop nodes? So then there's a next algorithm. It's called hits. So that's a hyperlink-induced topic search. So instead of using a transition matrix, it uses an adjacency matrix, because now we are going to look for both incoming edges and outgoing edges. So this is instead of a stochastic process. So instead of a transition matrix, we are looking at the adjacency matrix. Okay, so in this example, okay, so this is a it's supposed to be the example from the earlier page, but it has a one link missing. Okay, so it has a, so D1 goes to D3 and also goes to D4, right? So this is the earlier, it's supposed to be this, but then this, I copy these things from your textbook, so you should have another link here. Okay, so that's, you have this from D1, you go to D3 and D4. And from D2, you go to D1. From D3, you go to D2. And then from D4, you go to D2 and D1. Right, so that's the adjacency matrix. And then you just sum them up, the outgoing edges and the incoming edges for each page separately, so that the outgoing ones, I'm going to call it hop, right? So this is outgoing edges. So for each DI, I look at all the other pages, DJ, that come from I directly. So that's out of DI. And then in of DI, that goes into DI directly. So I'm going to call that authority. So then I have a hop, I have authority, and then I'm just going, I have this matrix A, right? So I have this matrix A. So what I do is I will iterate this, I will iterate these two, okay? But we also want to carry out a normalization. So the normalization is to make sure the sum of square is equal to 1. Okay, so that we care, so we normalize this, and then this should be a arrow indicates that this is a vector now. Yeah, I got this from the book, so sometimes it's not that consistent for notation you use in the book. Okay, so that's how you do an iteration. Then at the end, for each node, you have two. For each node, you have two values. One is the hop value, the other one is the authority value. Okay, so then so that means that it captures both hops and authority. So this is hits. It captures both, and the PageRank captures authority, and hits captures both. All right. So hits is not, it's used, but it's not as popular as PageRank. Okay, so once we have done these two algorithms, then the next thing would be, the next thing we would need to think about is how can we return a better rank lists, right? So you have a query, so it's a search engine. Now, once again, it's a search engine. I have a query, and according to the match, I have a rank list, but then you should also consider their individual ranking, right? So some of the documents, maybe I want, when I list them, in addition to their matching level, I'm also going to look at their page rank, right? So if a node has a higher rank, page rank, I should put it earlier. Similarly, if a page has a higher hits value, you sum them up. You sum them the hop and authority value, right? So that's one way you get its value. So if it's higher, then maybe I need to adjust my rank list when I return those documents to the user. Okay, so that is, so how do I do this, right? So how do I combine them? And a common approach is to use machine learning algorithm. Well, machine learning could mean different things. Here we just look at some simple combination of different features using logistic regression. Okay, so this is one approach. So we combine these features. So we know BM25 is to matching, right? This is the best match algorithm that we can use to match a document with a query, and query likelihood, right? So, and pivoted length normalization, as we know that PM25 and this PLN vector-based algorithm. We also could have the language-based, and we also have page rank, right? So we have, we rank these nodes independently of queries, and hits are independent of queries, and retrieval models to the anchor text, right? So you could just look at the anchor text, because the anchor text tells you, it's a concise description of what this particular document is about. So in order to match your query, if my anchor text has keywords that match your query, then probably I should give more weight on those pages. Right, so that's anchor text. So you have so many of these things, and then I want to combine them into one algorithm. Okay, so this is just like how I'm going to mix them up, right? So like cooking a meal, you get all these ingredients, and how you make a good meal is that you have to come up with a good proportion of each, good portion of each, or good percentage of each ingredient. So this is, so how can I mix them up? Mixing into one, or into a single algorithm. Okay, so for this, then we use machine learning in the sense that we know we are going to combine them. So we are going to pick an underlying combination. So we have, obviously, we can choose what kind of mixing scheme we are going to use. You can do a linear mixing, like a linear convex. So that means you have all these features. So this is a value, right? So it's a particular rank value for each document. You have all these this, then we get, we're gonna put a coefficient for it. So let's call it alpha 1, alpha 2. Say you have k many, then you're gonna just, so this is a linear convex combination, means that I'm going to give each of these a feature a weight, where when you sum them up, it's equal to 1, and each of these is between 0 and 1. So that's linear combination. But the better approach for this is to use logistic regression. Okay, so this is So logistic regression is you look at this. Okay, probability. So this is a probability approach. So this means that given query and given a document, that the relevant is 1. So in other words, this D is relevant to Q over 1 minus this probability, take log, and that can be written in this form. Okay, so you get these beta 0. So this is looks like you may think of it as some kind of approximation of using Taylor expansion. But anyway, so you can just write it down as this form. And the probability then, in this case, is for this is 1 over, now this is logistic regression. So it's 1 over 1 plus e to the negative of these things, of these things, right? Okay, so, but then whereas machine learning comes to play. So you have to determine what each of these value of beta will be. So if you have training data usually means in this case is label data. So you look at a query, you look at the documents returned, and the label means these are relevant, the other one is not relevant, and then you should also probably give them some, in addition just to relevancy, you probably want to give them some other indication how relevant it is. And then once you have these labels, we can train these parameters. So training in this case just means to learn parameters, okay, for the underlying representation of your mixing scheme. So I want to learn how to mix them. What's the portion of each feature? So you have to use label data to train them, means that to determine these values so that you get the best result. Best result means you get a higher F1 value, right? So that's one mechanism. So I get a higher F1 value. Or if you look at the error estimation, we use mean square estimation. So that should be the smallest. So minimize the square error or maximize the F1 score. So that's training. So how you're going to train them depends how your underlying mechanism will be. Okay, so we're not going to go too much, going in too much depth. Okay, so well, it's just an example to show off the calculation. Right? So it's really pretty straightforward. So once you have this table, let's say this table is what you are given of your label data. So you carry this out. So you got this B0 up to B3. You want to figure out what the value should be to best fit this best fit this label data. So basically that's it. All right, so and the last slide is just sort of talking about user data service triangle, because the ultimate goal for web search is to provide the best user experience to the users. Right? User wants it, I provide the best match documents, not just the best match means a lot of different things, right? So you have different algorithms we already talking about. We could mix them up to provide the best results to the user. Okay, so we need to always keep users in mind because they are the customers of a web search or web search engine. And then of course, in order to provide the best match, you would need to collect data, all kinds of data, right? So all kinds you need it. So that's user, because they are the customers of this system. In order to provide better service, you need to have better data collection, and you want to make your system easy to use. So that's a service. Okay, so it should be put these three things together for any good text mining system: users, data, and the system itself, right? So whether this is easy to use, whether this is efficient, and whether this is accurate. So these are the services. Okay, with that, I'm going to conclude this web search. So let me say a few more words before we start a new topic. Do I have time here? So I have about 15 minutes left. So let's go back to Blackboard. Okay. So how do I going back? Okay, so this is obviously an important module from my point of view, because that everything we talked about earlier, eventually we use them all in one platform that it's on the World Wide Web. So basically that's a lot of business are built on the World Wide Web, right? So then as I said, I mentioned last time, I included a few papers here. For instance, how do you handle a large inverted index? So we know we need to use GFS, Google File System, and MapReduce. So I included the original paper and some of the tutorial materials. And this is the PageRank original paper, and this is the HITS, the original paper. Okay, so if you're interested in this, or if you're doing a project, okay, and this could give you some idea. And again, as I said, we have discussion topics for each module. So I hope that you will not just ignore those, even though my answers to these topics will be posted. But from the learning perspective, if you don't really think about these things by just looking at my solutions, so the effect of learning may not be as good. But I'm not going to enforce you. So I'm just saying, okay, this is your choice, whether you participate in this discussion or not, but they do carry 5% weight towards your final. All right. So that's what I have for this module. Any question?
Yeah, I have one quick question on hits. Is there any reason why it's not used as much? Has it been shown to not be as efficient, or is it expensive?
Well, depends on what you are doing. So if you want to return a good result, the hits are still used. Hits are still used, but hits carry, as I said, hits captures both things, hops and pages. And if a page that the hop parts and the hop parts and the authority parts are probably the same, they don't give you much more extra value than you just doing the hop or just doing the PageRank.
Okay.
Does that make sense? Yeah.
Yeah, thank you.
Yeah. Okay. So it really depends on what you are doing. So I have seen people using hits to do something really interesting. But for here, it's just that a lot of pages, they are both hops and both authorities. If you cannot really distinguish them, then you spend time to computing them. It doesn't give you much more information. All right. Any other question? Okay, so I could start, but I guess I should just stop here and leave the next module to Wednesday. So next module is already open. So we're going to look at the last thing of this web service. So which is a recommender. So in other words, so you think of a search engine is is initiated by the user, right? So the user wants to search for something and presents queries. So then the recommender is from the system's point of view. So based on the user's behaviors, or you can capture the history, browsing history of a particular user and try to figure out what that user is interested in. So this topic is some kind of controversial to me because these systems are trying to learn you, right, as a person, even though they don't know your name, but they know your IP. So they would know, oh, this IP always does this, or interested in doing this. Now, how can I provide a better service to this IP? By providing better service, and most of the time it means they want to lure you to buy stuff so that they can charge you more. So that, I don't know whether that is really a good thing, but for commercial purpose it is, right? Because let's say we want to buy stuff. If we want to buy from, let's say from Amazon, then we are gonna, for each product we search for, we're gonna see user comments on that product. But from the system point of view, we can, let's say, it has been done, right? So sometimes you search for certain items, and suddenly when you open up with the web browsing, then similar items or similar advertisement pops up for you, right? So those belongs to this recommenders thing. Okay, so I don't know whether that is a good thing or not, but it is there, it exists. From the user point of view, it's also always a pros and cons, right? So you probably get something that you want, but sometimes it's very annoying, right? Annoying. And sometimes you know that you are losing your privacy. But once you're on the internet, you lose privacy anyway, right? So even though they may not know your true identity, but they know your IP address. They know what machines you use. They also know this account. You travel anywhere, they would know, right? Google knows you too, right? So if you use a Google phone, you travel around, they know where you travel. So but nevertheless, there are algorithms involved to make better recommendation. So that's what we're going to talk about. So after this module, so module 6, then we're going to do more on the text mining side. Right? So right now we are mostly on text retrieval side, right? But once you know how to get your data, then from those data, then I want to really get the information I want. So that will be after this module. All right. So I'm going to stop now. Any question? Okay, see you on Wednesday.
Thank you.
Bye-bye now.
Bye bye.